Okay, let me try and sort of sketch out what we were doing last time, because that was kind of complicated. So method of least squares. Method of least squares. So the main theorem was the following, that, and I'll just sort of draw a picture, that so in Rn, you have some subspace, so S, a subspace, right? So it passes through the origin, and then you have some vector B, then you have the direct sum composition. So Rn can be written as S plus S perp, right? Which means that B can be written as B sub S plus B sub S perp, right? So you can split this thing up into something in S, which we're calling B sub S, and something in S perp, which we're calling B sub S perp, right? And then the theorem said that the closest vector to B, the closest vector in S to B is uniquely B sub S, right? That guy is the closest, and there's nobody else that's closer. There's nobody else who has even equal distance. Right? Okay, so that was the theorem that we're going to use to solve the problem. Now, let's state the problem again. Recall the problem. The problem was, to solve the overdetermined AX equals B, right? So you wanted to solve this overdetermined system AX equals B, which was impossible. So you change the problem to find x hat such that AX hat minus B is smallest. Right? And then you say, well, and then you notice AX hat is in the range of A. AX hat is in the range of A, of course. So you can change the problem to find P in the range of A such that P minus B is smallest. Right? But then you see that then you see that you can change the problem again to saying that you know that this thing is going to be smallest, right? By the theorem, you know that this thing is smallest if and only if this thing is in RA perp. Right? You want the difference to be perpendicular, right? You want the difference to be perpendicular, and that would guarantee that. Right. Okay, but then you use the fundamental subspaces theorem. Fundamental subspaces theorem says that this is the same thing as the null space of A. Okay, so again, we changed the problem. We've now changed the problem to find P minus B in the null space of A, right? Okay. Okay, let me revert this P back to AX hat, right? Right, so remember our initial, what we're calling P is actually this AX hat, right? So we want X hat such that AX hat minus B is in the null space of A. In other words, A of, I'm sorry, null space of AT, this is wrong. Sorry, I messed up the fundamental subspaces there. This should be AT, A transpose, A transpose, A transpose. Okay, so we want X hat such that if we do this, then we get A transpose B, right? We want X such that A transpose A X hat equals A transpose B. Okay, so you see that basically we started off with this problem, which was impossible to solve. It had too many rows. Okay, too many rows. And then what we did was we multiplied everything by A transpose. Right? We said, well, that's impossible, but in fact, this is actually possible. Okay, there is something that solves this, and that's going to be the closest thing. The closest thing in the range of A to the parameters that we specified. Okay, so and we finished at that point by remarking that if ATA is invertible, then you can figure out then X hat is going to be ATA inverse ATB. And then AX hat is going to be A times that. So the AX, we can just leave this A out if you feel like it. Right? X is going to be this thing. X is going to be this thing. Of course, X hat is going to be this thing. AX hat is, of course, going to be A of the right-hand side. So, yeah, but pictorially, this thing is going to be your AX hat, right? AX hat, that's the P, that's the closest thing. Right. So this is the ATA inverse, ATA inverse A transpose B. That's going to be this thing here. Okay, let's do an example. So this example is in your book. So it says, find the quadratic function. Find the quadratic function that has the best least squares fit to the data 0, 3, 1, 2, 2, 4, 3, 4. Okay. So you have right? 0, 3, 1, 2, 2, 4, and 3, 4. Okay. So somebody's giving you 4 points and says, find me the quadratic function that passes through these 4 points. Okay, that's actually too many points, right? Because to specify a quadratic function, you need 3 points, right? So giving them 4 points makes it impossible, right? It's like saying, find me the line that passes through these 3 points, right? For a line, once you have 2 points, you've already specified the line. Adding a 3rd point just overdetermines the problem, right? So this is impossible, right? Clearly it's impossible. You're not going to find a quadratic that passes through all of these points. But you can find the best quadratic in the least squares sense. So observe. We want a quadratic p of x equals c naught plus c1x plus c2x squared, such that p of 0 is 2. I'm sorry, p of 0 is 3, p of 1 is 2, p of 2 is 4, and p of 3 is 4. Right? But that means that this is going to be c naught. This is going to be c naught plus c1 plus c2. This is going to be c naught plus 2c1 plus 4c2. This is going to be c naught plus 3c1 plus 9c2. Right. So this is the problem, right? We have 4 equations and we have 3 unknowns. Right? We've got 4 equations and 3 unknowns. It's overdetermined. So we rewrite this as so in other words, we want C naught, C1, C2, C3, such that, I'm sorry, C naught, C1, C2, such that 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9, times C naught, C1, C2 equals 3, 2, 4, 4. Okay, so this is an overdetermined system. We don't know, we can't solve it. So what we do is we change it to this problem, right? This is our AC equals B, right? We're going to change it to ATA equals ATB. Then ATAC equals AB, oops, ATB. Well, that turns out to be, you multiply both sides by the transpose. So 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9, times that 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9, C naught, C1, C2 equals 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 3, 9 times 3, 2, 4, 4. Right. And that, if you work it out, it looks like this: 4, 6, 14, 6, 14, 36, 14, 36, 98, C naught, C1, C2 equals 13, 22, 54. Okay, and then you solve it, and you get that, you solve it just using Gaussian elimination. You get C naught is equal to 2.75. C1 turns out to be negative a quarter, and C2 turns out to be positive a quarter. Okay. And so those are the coefficients that that give you the best approximation. In this sense. Okay, so remember that it just well, actually, everybody see how to do it. Everybody see how to do it, right? All you do is you start off with your system that's overdetermined, and then you solve. You multiply by A transpose, and then you solve that system. Okay, so. The hard part was the theory behind it. Right, which involved direct sums, fundamental subspaces there. Just a side comment. You notice that what we're doing, we're minimizing. We're trying to minimize this norm, right? This distance between these two things, and this is dependent on how we define the distance. So if you define distance in a different way, you get a different answer. So like a lot of machine learning is basically trying to find the best answer by minimizing a certain kind of error, but not necessarily the Euclidean error, but some other error. Yeah, Izzy.
Then could you use kind of the theory behind it to figure out what that error would be? Because you kind of said that AC was the same thing as that P, which was the B of the subspace.
Mm-hmm.
Is there then another way to then get the B of the subspace perp, which would then find the most error in a sense?
So a different kind of perp is what you're
Yeah.
saying? Yeah. Wait. I think it's not so. It's true that if you change the inner product, then you're going to get a different kind of perp.
Uh-huh.
Yeah, and then so that would give you a different kind of error. So yeah, that's true.
Okay.
Yeah. Okay. Okay. I hope that's clearer now than it was before. Just a couple of comments to close up this chapter. Remark one, as we said before, if ATA is invertible, then that P, turns out to be, ATB hit with the inverse of ATA, hit with A. Right. So again, the picture was if this is B, then P is going to be that thing, right? Because this thing was x hat. Right. And so that's kind of nice because what it tells you is that we sort of therefore call this thing ATA inverse AT the projection operator. Of Rn onto Ra. Okay, because you see what it does, right? If we call this thing, I don't know, I think we called it capital Pi, capital P last time, right? What does it do? It takes any vector and then projects it to the nearest guy, right? So it basically it looks at the shadow, and this is going to be pi of v here. So it takes your vector and then puts the shadow onto the range of A. So that's one thing that's useful, and that shows up in your homework. Second thing to remark is that if the rank of A is n, then in fact ATA. So remember, A is an m by n matrix. If the rank of A is n, then ATA is invertible. Okay, let's see why. Let's see why that's true. Consider, okay, so first let's think, first notice the rank of A is n. What does that tell you? If the rank of A is n, then what do we know?
The nullity is 0.
The nullity is 0, great. Nullity is 0. In other words, the null space is just the 0 vector. The only thing that gets killed is the 0 vector. Okay. So we want to show that ATA is invertible. That's the same thing as saying that the null space of ATA is 0. The null space of ATA is going to be we want to show that the null space of ATA is 0. So let's think. Right. Suppose you have a vector x such that ATAX equals 0. Okay. We're hoping that guy turns out to be 0. Okay. Well, in that case, AX is in the null space of A transpose. But fundamental subspaces theorem, you can guess we're going to use it. Null space of A transpose is the range of A is perpendicular to the range of A. Okay, so why is x 0? Who wants? Anybody want to say? Sasha?
No, I haven't like completely, but
That's okay.
if AX is in RA perp,
Mhm.
well, it's also in RA just because
Exactly.
look at it, but if it's in both of them, then that means that obviously it has to be 0. And then I mean, A isn't 0.
Right, so AX equals 0, right? So why is X 0?
I hadn't gone quite there.
Anybody see why X must be 0?
Because the null space of A is 0.
Because the null space of A is 0,
Yeah.
right? Because the rank was n, right?
Yeah.
So X must be 0. Okay. Okay, so that just gives you a condition, you know, that, we introduced this projection operator. Projection operator you can use when this thing is invertible, and then here's a condition that gives you when that thing is invertible. So like if the rank is n, then you can actually define a projection operator. Okay, so that's it for section 5.3, least mean squares, which is a pretty important one in terms of its application. Okay. 5.4. All these tiny pieces. 5.4 is what's called inner product spaces. Okay, so this is basically a generalization of dot products to abstract vector spaces, right? So, what we've been talking about so far in this chapter is, you're in Euclidean space, you have the dot product, and then you have all these results and stuff. Okay, but it turns out that just like how we extended Euclidean spaces to abstract vector spaces, you can extend dot product to inner product. Okay, so basically, like many familiar phenomena in Rn can be extended to abstract vector spaces. So familiar, like maybe I should say familiar geometric phenomena, like the Pythagorean theorem or this sort of thing. So what we need to do first is to sort of create something that's like the dot product. Basically, it will have all the properties of the dot product that are necessary to generalize these things that we like. So. Suppose you have a vector space, okay, and then you have this thing going from V cross V to R. Okay, so you have what's called a binary operation on V. Okay, so it takes in 2 vectors and returns a number. Okay, takes in two vectors and then returns a number. So it's just like the dot product, right? The dot product takes 2 vectors and then gives you back a number. Okay, so right, it's like instead of writing u dot v, I'm going to write u bracket u comma v. Okay, so you have this binary operation that satisfies three things. So, so suppose you have, so given a vector space and a binary operation, if one so if three things happen, then we call this binary operation an inner product on V. Call it an inner product V on V, and we call V with that inner product an inner product space. Okay. Okay, and so the three things that you want are that, one, that when you take the product of anything against itself, it's bigger than or equal to 0. Right? That certainly happens with the dot product. Right? When you take the dot product of something against itself, you get something that's non-negative. Right? Further, it should be that you get 0 if and only if V is the 0 vector. Okay, right. You want your inner product to have this property that the only time you get 0, is when the only time when you get 0 when you dot against yourself is if the vector is the 0 vector.
I have a notation question.
Yeah.
So when you said it was equals, you like left it as like kind of the brackets and the equals on the outside. When you did the greater
Oh, I'm sorry.
than.
That is just.
Oh, okay.
Sorry.
Cool. That makes more sense.
Yeah, thank you. Okay, I hope it makes sense now.
Yeah.
Okay. Second thing you want is that, if you take the dot product in one direction, it's the same thing as taking the dot product in the other direction. So if multiplication is commutative. This multiplication is commutative. Okay, so all u v. Okay. And then the third thing you want is that if you take some linear combination and dot it against a vector, then what am I going to write over here? What should that be? Based on your knowledge of the dot product, what should I write over here? Sasha?
Z1 alpha x plus Z2 beta y. Wait.
Not quite. So just think, if I have like a vector, one vector and another vector, and then I dot them against a third vector, w, right? What's going to happen?
Is the sum of like, it'd be like a linear combination, but like including the third vector. Wait, no, I need to work right now.
Yeah, well, I'm sure you know what you want to. It's basically going to distribute.
Yeah.
It's going to distribute. So you get like alpha times x against z, and beta y against z. Right. So this is what we call linearity. Linear in the first variable. Linear in the first variable. We don't need to specify that it's linear in the second variable because of commutativity. It's because of commutativity, it's automatically linear. If it's linear in the first variable, it's going to be linear in the second variable. Okay, so this is just a definition, right? It says that, if you have this kind of operation and it behaves like a dot product, it has these three properties that we like of dot product, then we call it an inner product. We call this space an inner product space. Let me give some examples. Of course, if V is Rn and x, y is x transpose y, well, then that's an inner product space, right? Because that's the dot product. Right? The inner product space is a generalization of the dot product. This is just the dot product. So that is an inner product space. We know that it satisfies all these properties. Kind of variant of it is if you let V be Rn, and if you have what we call a weighting vector, where Wi is greater than 0 for all I. Okay, so W is some vector, W1 through Wn, but all these things are positive numbers. Okay. Now we define a weighted dot product as summation xi, yi, wi. So it's like the dot product, but each component is weighted differently. Okay, you're allowed to say like, the first component I assign a tiny weight. The second component I give this huge weight. It's sort of like biasing things. Like I count this person's opinion more than this person's opinion. Okay. So this weighted dot product turns out to be an inner product. So weighted dot product is an inner product. You could define a dot product on matrices. So if you have like some A and B that are matrices of the same size, n by n, well, you could just sum up all the Ij, Bij's. Sum up all the, just take the products of all the corresponding entries and then sum that thing up. That's a dot product. And similarly, you could weight them. This is basically the same thing as this thing. It's just instead of putting it in a square, we're putting it in a line. Yeah, easy.
So for the weighted dot product,
Yeah.
is that something that like, if you like wanted more of this, you construct like the vector W so that it like purposely weights this more than that?
Yes.
Okay.
Yes. Yeah. Now, for something a bit more abstract, suppose you have the continuous functions on a closed interval AB. Okay, so continuous functions on AB. Then you could define you can define a dot product on functions. So let's say you have two continuous function on AB. You can define this sort of thing. So you take the integral of the function against the other function. So you integrate one function against the other function, and that actually turns out to be an inner product. And as usual, if you have some W that's in V such that W is always greater than 0, then you can create a weighted dot product, weighted inner product by integrating one function against the other, but also with some weight. So, like maybe you want to emphasize certain parts of the interval. Okay. So this is cool, right? Because now we're thinking of not just vectors and stuff like that, but we can think of functions, right? Think about like the inner product of functions against each other. Last example, let W be the polynomials of degree less than n. Okay. So remember, polynomials of degree less than n. So fix any endpoints x1 to xn in R. So they have to be different points. So distinct points x1 through xn. And then we can define the inner product. So for P and Q that are polynomials of degree less than n, let the inner product be the sum of Pxi, Qxi, as I ranges from 1 to n. Right. And again, you can weight. You can also create a weighted version. So that turns out to be an inner product also. That turns out to be an inner product also. So I'm kind of cheating you here because I'm just saying like this is an inner product, that's an inner product, this is an inner product, that's an inner product, right? All of these facts, all of these things need to be checked, right, to see that they actually satisfy the three properties, right? Like, why is it true? Some of it's kind of obvious, right? Like if I switch the order here, does it change things? No, right? Because you're just integrating numbers are commutable. Multiplication of numbers is commutable, right? Right. If this thing is, if I take f against f, do I get something positive? Sure, because I'll be getting the integral of f squared, right? F squared is going to be greater than or equal to 0, so I'm integrating something greater than or equal to 0, right? Now, is it true that the only way I can get 0 is if f is 0? If the inner product of f against itself is 0, does that mean that f must be 0? Well, that's actually a little trickier because that really relies on the continuity. Because you'd say, well, look, if f were not 0 at some point, then there would be a little bump in the area. Because of continuity, there'd be this little bump in the area, right? And so that would cause the integral to be bigger. So the only way you can get 0 by integrating the function against itself is if the function is 0. If the function were non-zero somewhere, then this thing would be bigger than 0. So that's a little bit more subtle. Right. What about this one? If the integral of a polynomial, I'm sorry, if you have summation p xi, pxi, and that equals 0, do you know that p must be 0? P must be the 0 polynomial? This was kind of a tricky one. So this sum being 0 means that p at xi is 0, right? For each of those xi's, right? So that would mean that you've got these endpoints, right? x1 to xn, and you know that your polynomial is 0 at each of those points, right? Your polynomial is 0 at each of those points. Does that force the polynomial to be 0 everywhere? Yes. because the polynomial is of degree less than n, right? It's a less than n degree polynomial, and it's got n points that are 0. That actually is enough to force it to be 0. So that, you know, some of these things require a little bit of thought. Okay, so I'm just gonna leave them as just like that. Okay, so we'll get back to this next time, and look at like, yeah, properties. You know, what can we do in inner product spaces that we could do in Euclidean space? Okay, that's it.
Thank you.
Okay, you're welcome.
Thank you.
You're welcome. Bye-bye, you're welcome. Yes.
Did you post which homework problems we're doing for this week yet?
Did I not? I thought I did.
Well, I don't know if you did, I was asking.
Okay, I
have
believe
ones.
I believe I did yesterday.
Okay,
Yes,
awesome.
I believe I did yesterday.
Great, thank you.
Okay, you're welcome. See you.